Hello, and welcome to tonight's atmospheric journey. I'm the drowsy professor, and together we'll explore one of nature's most comforting mysteries: why the vast ocean of air above us never comes tumbling down. As you settle beneath this invisible protective embrace that surrounds our planet, let me know where in the world you're resting and what time the evening has brought to your corner of Earth. Now, sink deeper into your most comfortable position. Feel the gentle weight of blankets settling around you like layers of atmosphere, and let's drift together into the peaceful science of our sky's eternal suspension. Imagine for a moment that you could see the air around you. Picture it as a vast, invisible ocean stretching from where you lie all the way up to the edge of space itself. This ocean of atmosphere that surrounds our planet weighs approximately 5.5 quadrillion tons. A number so large it becomes almost meaningless until you consider that this entire massive envelope of air simply floats above us, held in perfect suspension without ever falling to crush the world below. Take a slow breath and feel that air flowing into your lungs, each molecule a tiny traveler that has journeyed through this atmospheric ocean, perhaps circling the globe countless times before finding its way to you in this quiet moment. The air you're breathing right now carries with it the weight of everything above. Miles and miles of atmosphere pressing down from heights that stretch beyond the reach of the tallest mountains, beyond where commercial aircraft fly, beyond where weather occurs, all the way to the thin boundary where our planet's breath finally meets the vacuum of space. Yet as you lie there, you feel no crushing weight, no sense of being pressed down by this enormous mass of air that extends in an unbroken column from your chest to the very edge of Earth's influence. The pillow beneath your head supports you gently. Your breathing flows easily and naturally, and the only pressure you might notice is the comfortable weight of your covers and the soft support of whatever surface holds you in this moment of rest. This absence of crushing weight might seem mysterious at first. How could something so massive simply hover above us without falling? The answer lies in one of nature's most elegant solutions, a perfect balance of forces that has been maintained for billions of years, creating the stable, protective environment that makes life on Earth possible. Understanding this balance requires us to think differently about weight, pressure, and the very nature of the gas that surrounds us. Picture yourself standing outside on a calm day, feeling the gentle breeze against your skin, watching clouds drift lazily across the sky. Those clouds, made of countless water droplets suspended in air, seem to float effortlessly despite being composed of water that would certainly fall if it weren't somehow held aloft. The cloud's ability to float gives us our first clue about the nature of atmospheric suspension. The air itself is constantly in motion, constantly pushing and supporting in ways that aren't immediately obvious to our senses. When you step outside, your body is surrounded by air molecules moving in all directions at speeds that would amaze you if you could perceive them directly. These molecules, invisible and largely unnoticed, are bouncing off every surface of your body thousands of times per second, pushing against you from above, below, and all sides with equal force. The pressure they create pushing up against the bottom of your feet exactly balances the pressure pushing down on the top of your head, creating a perfect equilibrium that leaves you feeling weightless despite being immersed in this ocean of moving air. The weight of the atmosphere, enormous as it is, becomes distributed across the entire surface of our planet in such a way that each square inch of Earth's surface supports only about 14.7 pounds of atmospheric weight. This might sound like a lot, but it's distributed so evenly and balanced so perfectly by upward pressure that you never feel it as a burden. Your body has evolved within this pressure environment, with internal pressures that perfectly match the external atmosphere pressure, creating a state of balance that feels completely natural and comfortable. Consider how this atmospheric weight changes subtly as you move through your daily life. When you ride in an elevator, your ears might pop slightly as you ascend or descend, responding to tiny changes in atmospheric pressure as you move through different levels of the air column above you. When you drive up a mountain, you might notice your ears popping more frequently, or you might feel slightly out of breath as the weight of atmosphere above you decreases and the air becomes thinner. These small changes in pressure give you direct experience of the atmosphere's weight, but they also demonstrate how beautifully our bodies adapt to variations in this aerial ocean. Your circulatory system adjusts to different pressures. Your lungs modify their function to extract oxygen efficiently at various altitudes, and your inner ear maintains balance despite pressure changes. All of these adaptations happen automatically without conscious effort, showing how perfectly life on Earth has evolved to exist within our planet's atmospheric embrace. The weight of air becomes more noticeable during weather changes, when shifts in atmospheric pressure create the phenomena we experience as storm systems, wind patterns, and the various weather conditions that make each day unique. When a storm approaches, the atmospheric pressure often drops, and you might feel this change as a subtle sensation in your joints, a slight headache, or simply a vague awareness that the air feels different somehow. During these pressure changes, you're experiencing the weight of the atmosphere in motion, as vast columns of air move across the landscape like slow, invisible rivers. High-pressure systems bring dense, heavy air that settles over regions like a comfortable blanket, while low-pressure systems create areas where the atmospheric weight is reduced, allowing air to rise and creating the circulation patterns that generate clouds, precipitation, and wind. Picture the atmosphere as a vast, three-dimensional ocean with currents and tides, areas of density and lightness, regions where the air piles up like underwater mountains, and valleys where it thins out like aerial canyons. This atmospheric topography is constantly shifting and changing, but always maintaining the overall balance that keeps our sky suspended above us rather than collapsing under its own enormous weight. The comfort you feel as you rest here tonight is partly due to this atmospheric stability. The air pressure around you is being maintained at levels that support comfortable breathing, that allow your body's internal pressures to remain balanced, and that create the stable environment necessary for restful sleep. The weight of the atmosphere, rather than being a burden, becomes a protective presence that shields you from the vacuum of space while providing the pressure environment your body needs to function properly. As you continue to breathe slowly and naturally, each inhalation brings air that has been part of this suspended ocean for billions of years. The oxygen molecules entering your lungs may have been breathed by countless other living things, may have been part of ancient atmospheres, may have traveled around the world many times before reaching you. Yet despite this incredible history and the vast weight of air they represent, they flow into your lungs easily and gently, supported by the same forces that keep our entire sky suspended in perfect balance above the Earth. The secret to understanding why our massive atmosphere doesn't collapse lies in recognizing that air, despite being invisible and seemingly insubstantial, behaves much like a fluid that can provide support and resistance. Just as you can float in water because the water pushes up against your body with enough force to counteract your weight, the atmosphere supports itself through the constant upward pressure created by the motion and compression of air molecules throughout the entire atmospheric column. Picture yourself lying in a warm bath, feeling how the water supports your body and makes you feel lighter despite the fact that water itself has weight and presses down on you from above. The water beneath you pushes upward with exactly the right force to balance the water above, creating a state of suspension that feels effortless and comfortable. The atmosphere works in a remarkably similar way, with the air beneath constantly pushing upward to support the air above, creating invisible pillars of pressure that hold up our entire sky. These invisible pillars of air pressure are created by the fundamental behavior of gas molecules under the influence of gravity and heat. Every molecule of air in our atmosphere is constantly moving, bouncing off other molecules and off surfaces in random directions at speeds that depend on temperature. When these fast-moving molecules are confined within Earth's gravitational field, they create pressure by colliding with everything around them, including the air molecules above and below them. Imagine watching an invisible dance where trillions upon trillions of particles are bouncing against each other in every direction simultaneously. Each collision creates a tiny push, and when you add up all these countless tiny pushes happening throughout the entire atmosphere, the cumulative effect creates enough upward force to support the weight of all the air above. It's like having countless microscopic springs beneath every portion of the atmosphere, each one compressed just enough to provide exactly the support needed. The temperature of our atmosphere plays a crucial role in maintaining these invisible pillars of support. Warm air molecules move faster and collide more frequently, creating higher pressure and stronger upward force. Cool air molecules move more slowly and create less pressure. This temperature variation throughout the atmosphere creates a complex system of pressure differences that drive circulation patterns while maintaining the overall support structure that keeps our sky aloft. Picture the way heat from the sun warms the Earth's surface, which in turn warms the air near the ground. This warm air becomes more active, with molecules moving faster and pushing against each other more vigorously. As this energetic air pushes upward, it creates rising columns of warm, lower-pressure air that help to lift and support the cooler, denser air above. This process happens continuously all around the planet, creating a global network of thermal support pillars that help hold up our atmosphere. During the day, as solar energy heats different parts of the Earth's surface at different rates, you can sometimes see evidence of these invisible support pillars in the form of rising thermals that carry birds effortlessly upward or create the updrafts that allow clouds to form and persist in the sky. These visible signs represent just a tiny fraction of the thermal activity that's constantly occurring throughout the atmosphere, creating the pressure variations that support our sky suspension. At night, when surface heating decreases, the atmosphere doesn't collapse because the thermal energy stored in air masses continues to drive molecular motion, while the overall temperature differences between various atmospheric layers maintain the pressure gradients necessary for suspension. The atmosphere has enormous thermal inertia, meaning it changes temperature slowly and maintains its supportive pressure structure even when the immediate heat source is reduced. Consider how the pressure changes you sometimes feel in your ears during weather changes or altitude changes represent tiny fluctuations in these invisible support pillars. When you experience ear popping, you're feeling your body's response to small changes in the atmospheric pressure structure, variations in the strength of these invisible pillars that normally support our sky so reliably that we never notice them. The beauty of this atmospheric support system lies in its self-regulating nature. If air pressure in any region becomes too low, surrounding air immediately moves in to equalize the pressure, like invisible reinforcements rushing to strengthen a weak point in the support structure. If pressure becomes too high in any area, the excess air spreads out to regions of lower pressure, distributing the load evenly across the atmospheric system. Picture this pressure equalization happening constantly all around you, with air moving horizontally and vertically in response to tiny pressure differences, creating a dynamic, three-dimensional support network that adjusts itself automatically to maintain the proper balance. This movement of air in response to pressure differences is what we experience as wind, but at its fundamental level, it represents the atmosphere's constant self-adjustment to maintain the pressure structure that keeps our sky suspended. The molecular activity that creates these pressure pillars never stops, never takes a break, never requires maintenance or conscious control. Even as you rest quietly tonight, trillions of air molecules around you are bouncing against each other billions of times per second, creating the constant upward pressure that holds up the vast weight of atmosphere above. This molecular activity is powered by thermal energy that comes ultimately from the sun, but also from the Earth's internal heat and from the kinetic energy stored in atmospheric motion patterns. The scale of this invisible support system is truly remarkable when you consider it fully. Every cubic inch of air around you is pushing against every adjacent cubic inch with precisely the right force to maintain atmospheric suspension. Every breath you take removes a tiny amount of air from this support system, but the pressure equalizes so quickly that there's no measurable effect on the overall stability. Every movement of air due to wind or weather represents a local adjustment in this global support network. As you continue to breathe slowly and peacefully, you're participating in this vast system of atmospheric support. The air you exhale adds its tiny contribution to the molecular motion that creates pressure, while the air you inhale is immediately replaced by surrounding air moving in to maintain pressure equilibrium. Your breathing, quiet and gentle as it is, represents a small part of the constant molecular activity that keeps our sky suspended above us. The invisible pillars of air pressure that support our atmosphere extend from the surface where you rest all the way up to the edge of space, gradually weakening with altitude as the air becomes thinner, but never completely disappearing. Even at the very top of our atmosphere, where air becomes so thin it's barely detectable, there's still enough molecular motion to create the tiny amount of pressure needed to support the virtually weightless wisps of air that mark the boundary between Earth's atmosphere and the vacuum of space. These pressure pillars work together like the invisible framework of a vast cathedral dome, with each section supporting the others in a structure so perfectly balanced that it has remained stable for billions of years. The dome of our sky, held up by nothing more substantial than the motion of invisible molecules, provides a more reliable and enduring shelter than any structure humans have ever built. Tonight, as you drift towards sleep beneath this invisible cathedral of suspended air, you can rest in the knowledge that the same molecular forces that have supported our sky for eons will continue their tireless work, maintaining the atmospheric pressure that keeps our protective envelope of air floating peacefully above you, never falling, always suspended in perfect balance. To truly understand why our sky remains suspended above us, we must journey into the invisible realm of molecular motion, where the real magic of atmospheric suspension takes place. Every breath you take contains approximately 25 sextillion molecules, a number so vast that if you could count one molecule per second, it would take you longer than the age of the universe to count them all. Each of these molecules is engaged in a constant, frenzied dance of motion that creates the forces responsible for keeping our entire atmosphere aloft. Picture these molecules as incredibly tiny dancers, each one smaller than anything you could ever see, moving at speeds that would astound you if you could perceive them directly. At room temperature, the average air molecule travels at roughly 1,100 miles per hour, faster than the speed of sound, bouncing off other molecules and changing direction thousands of times per second in a completely random pattern that creates what scientists call Brownian motion. As you rest comfortably in this moment, you are surrounded by this invisible molecular ballet, with every cubic inch of air around you containing roughly 400 billion molecules, each one moving at tremendous speed in completely unpredictable directions. They collide with each other, with your skin, with every surface in the room, creating billions upon billions of tiny impacts every second. These collisions are so small and happen so frequently that your senses can't detect individual impacts. But their cumulative effect creates the pressure that supports not only your body, but the entire weight of our atmosphere. The kinetic energy of these moving molecules, the energy they possess simply by virtue of their motion, is what prevents our atmosphere from collapsing under its own weight. Each molecule carries a tiny amount of kinetic energy, but when you multiply that energy by the astronomical number of molecules in our atmosphere, the total energy involved becomes enormous. This kinetic energy manifests as pressure, as heat, and as the constant outward push that balances the inward pull of gravity. Imagine trying to compress a balloon filled with air. As you squeeze, you can feel the resistance created by the air molecules inside pushing back against your hands. The harder you squeeze, the greater the resistance becomes, because you're forcing the molecules into a smaller space where they collide with each other and with the balloon walls more frequently. This same principle operates throughout our entire atmosphere, with gravity acting like invisible hands trying to compress the air, while the kinetic energy of molecular motion provides the resistance that prevents compression. The temperature of our atmosphere directly controls the speed of molecular motion, and therefore the strength of this resistance to gravitational compression. Warmer air contains molecules moving faster, creating higher pressure and stronger resistance to compression. Cooler air contains slower-moving molecules, creating lower pressure and less resistance. This temperature-dependent molecular motion creates the complex pressure variations that drive weather patterns while maintaining the overall atmospheric stability that keeps our sky suspended. During the day, when solar energy heats the Earth's surface and the air above it, molecules near the ground begin moving faster, colliding more frequently, and creating increased pressure that helps lift and support the air above. This thermal acceleration of molecular motion creates rising currents of warm air that carry energy upward through the atmosphere, distributing the molecular motion that maintains atmospheric suspension throughout the entire vertical column of air. Picture the way heat from a candle flame causes the air above it to shimmer and rise. This visible disturbance represents millions of air molecules that have been accelerated by thermal energy, moving faster and more chaotically, creating the buoyant force that lifts warm air upward. This same process, repeated on a massive scale across the entire planet, creates the thermal circulation patterns that help support our atmosphere's weight while distributing molecular energy throughout the atmospheric system. The molecular motion that suspends our atmosphere operates on multiple scales simultaneously. Individual molecules bounce randomly in all directions, but their collective behavior creates measurable pressure and temperature patterns. Groups of molecules move together in currents and circulation patterns, but these organized motions are themselves made up of countless individual molecular movements. This multi-scale organization allows the atmosphere to maintain both local stability and global circulation patterns. As you breathe slowly and naturally, you're participating directly in this molecular dance. Each inhalation draws millions of fast-moving molecules into your lungs, where they transfer their kinetic energy to your bloodstream before being exhaled back into the atmospheric system. The oxygen molecules that your body extracts from the air carry with them a tiny portion of the kinetic energy that helps keep our sky suspended, connecting your very life processes to the forces that maintain atmospheric stability. The remarkable thing about molecular motion in our atmosphere is its consistency over time. Despite the seemingly random nature of individual molecular movements, the statistical behavior of large groups of molecules becomes highly predictable. Temperature, pressure, and density all represent average properties of molecular motion that remain stable even though individual molecules are constantly changing speed and direction in completely unpredictable ways. Consider how the air pressure around you right now is being maintained by the collective motion of molecules that are individually behaving in completely random ways. It's as if trillions of dancers, each moving without any coordination or plan, somehow create a perfectly choreographed performance that maintains precise timing and positioning. This emergence of ordered behavior from random individual actions represents one of the most beautiful examples of statistical mechanics in nature. The energy that drives this constant molecular motion comes from multiple sources, creating a sustainable system that can maintain atmospheric suspension indefinitely. Solar radiation provides the primary energy input, heating air molecules and accelerating their motion. The Earth's internal heat, generated by radioactive decay and leftover heat from planetary formation, also contributes thermal energy to the atmospheric system. Additionally, the kinetic energy already present in atmospheric motion patterns helps maintain molecular movement through a kind of atmospheric momentum. During nighttime hours like now, when direct solar heating is reduced in your part of the world, the molecular motion that maintains atmospheric pressure continues thanks to the enormous thermal inertia of the atmosphere. Air masses retain heat and molecular motion for hours or days after being heated, creating a buffering effect that maintains atmospheric stability even when immediate energy input is reduced. The thermal energy stored in the world's oceans also helps moderate atmospheric temperature and maintain the molecular motion necessary for atmospheric suspension. The molecular dance that keeps our sky aloft operates according to fundamental physical laws that have remained constant for billions of years. The kinetic theory of gases, which describes how molecular motion creates pressure and temperature, provides a reliable framework for understanding atmospheric behavior. These laws ensure that as long as our atmosphere retains thermal energy and molecular motion, it will continue to resist gravitational compression and remain suspended above the Earth's surface. Picture the molecular motion around you as a three-dimensional symphony of movement, with each molecule following its own unpredictable path while contributing to the overall harmonic pattern that creates atmospheric pressure. Fast-moving molecules create higher notes in this invisible symphony, while slower molecules contribute lower tones. Temperature changes alter the tempo of the molecular music, while pressure variations change its volume and intensity. The scale of molecular motion in our atmosphere becomes even more remarkable when you consider that every molecule is simultaneously affected by and affecting every other molecule in its vicinity. Each collision between molecules transfers energy and momentum, creating a vast network of molecular interactions that extends throughout the entire atmosphere. Your every movement, every breath, every change in body temperature creates tiny ripples in this molecular network that propagate outward at the speed of sound. As molecular motion continues its tireless work around you, maintaining the pressure that keeps our massive atmosphere suspended, you can appreciate the elegant efficiency of this natural system. No conscious control is required, no maintenance is needed, no external intervention is necessary. The fundamental properties of matter and energy, operating according to universal physical laws, create and maintain the atmospheric suspension that has protected and sustained life on Earth for billions of years. The molecular motion that prevents our sky from falling operates at every level of the atmosphere, from the dense air near Earth's surface all the way up to the thin wisps of gas at the edge of space. Even in the uppermost reaches of our atmosphere, where air becomes so thin that molecules might travel miles before colliding with another molecule, their motion still contributes to the overall pressure structure that maintains atmospheric suspension. Tonight, as you settle into deeper rest, the molecular dance continues around you with undiminished energy and precision. Trillions of invisible particles maintain their constant motion, creating the pressure that supports our sky, generating the thermal circulation that distributes atmospheric energy, and sustaining the stable environment that allows you to breathe easily and sleep peacefully beneath our planet's suspended ocean of air. The kinetic energy of these molecules, accumulated over the entire atmosphere, represents one of the largest energy reservoirs on our planet. This energy is constantly being exchanged, redistributed, and renewed through solar heating, thermal circulation, and molecular interactions, creating a dynamic equilibrium that has remained stable enough to support life for eons while continuing to adapt and respond to changing conditions. Rest peacefully in the knowledge that this molecular dance will continue throughout the night and far beyond, maintaining the atmospheric pressure that keeps our protective sky floating gently above you, supported not by any solid foundation, but by the ceaseless motion of invisible particles that transform the simple kinetic energy of movement into the complex, stable system that shelters our entire world. It might seem contradictory to suggest that gravity, the very force that pulls everything downward toward Earth, actually helps keep our atmosphere suspended rather than causing it to fall. Yet gravity plays a crucial and beautiful role in maintaining atmospheric stability, working not as a destructive force that threatens to collapse our sky, but as a gentle organizing influence that helps create the very pressure gradients and circulation patterns that keep our atmosphere aloft and stable. Picture gravity not as a harsh downward pull, but as a gentle, constant embrace that holds our atmosphere close to Earth while allowing it to maintain its suspended structure. Without gravity's influence, our atmosphere would simply drift away into space, molecule by molecule, until Earth became as airless as the Moon. Gravity's pull is strong enough to prevent this atmospheric escape, but gentle enough to allow the molecular motion and pressure dynamics that create atmospheric suspension to operate freely. The gravitational field that surrounds our planet creates what scientists call a potential energy well, Imagine Earth sitting at the bottom of an invisible bowl-shaped depression in space, with the sides of the bowl representing the strength of gravitational attraction at different distances from the planet's surface. Our atmosphere exists within this gravitational bowl, held close to Earth but not crushed against its surface because the molecular motion we explored earlier provides just enough outward pressure to balance gravity's inward pull. As you rest comfortably tonight, you can feel gravity's gentle influence in the way your body settles into whatever surface supports you. This same gravitational force is simultaneously holding every molecule of air in our atmosphere within Earth's gravitational embrace, while allowing those molecules the freedom to move and create the pressure that maintains atmospheric suspension. It's a perfect balance between containment and freedom, between holding and releasing. The way gravity varies with altitude creates one of the most important factors in atmospheric suspension. At Earth's surface, gravitational pull is strongest, creating the highest air density and pressure. As you move upward through the atmosphere, gravity's pull gradually weakens, allowing air to become progressively less dense and creating the pressure gradient that helps support the weight of air above each level. This gravitational gradient is essential for maintaining atmospheric structure. Consider how this gravitational variation affects your daily experience. When you climb stairs or ride in an elevator, you're moving through slightly different levels of gravitational influence, experiencing tiny changes in the force that holds our atmosphere together. Your ears might pop during rapid altitude changes because you're moving through the pressure gradients that gravity helps create and maintain throughout the atmospheric column. The gravitational compression that affects our atmosphere operates very differently from mechanical compression. Instead of simply squashing air into a thin layer against Earth's surface, gravity's influence decreases gradually with altitude, creating a compression gradient that becomes gentler and gentler as you move upward. This graduated compression allows our atmosphere to maintain its extended vertical structure while still being held securely within Earth's gravitational influence. Picture the atmosphere as a vast, invisible fountain, with gravity providing the gentle downward force that gives the fountain its shape and structure, while molecular motion provides the upward energy that keeps the fountain flowing and prevents it from simply collapsing into a puddle at the bottom. The interaction between these two forces, gravity's organizing influence and molecular motion's dispersive energy, creates the stable, suspended structure of our atmospheric fountain. Gravity's role in atmospheric circulation adds another layer to its contribution to atmospheric suspension. The uneven heating of Earth's surface by solar radiation creates temperature differences that, combined with gravity's constant downward pull, generate the circulation patterns that help distribute atmospheric mass and energy. Warm air rises because it becomes less dense and experiences less gravitational pull per unit volume, while cool air sinks because it becomes denser and experiences stronger gravitational attraction. These gravity-driven circulation patterns help prevent our atmosphere from developing the kind of instabilities that might lead to collapse or escape. Instead of allowing air to accumulate in stagnant layers that might become unstable, gravitational circulation ensures that atmospheric mass is constantly being redistributed, mixed, and renewed. This circulation process helps maintain the dynamic equilibrium that keeps our sky suspended in stable configuration. As you breathe slowly and peacefully, you're experiencing the direct effects of gravity's atmospheric embrace. The air pressure that makes breathing comfortable and natural exists because gravity holds our atmosphere close to Earth while allowing molecular motion to create the pressure gradients necessary for respiratory function. Your lungs extract oxygen from air that has been organized and compressed by gravity into the precise density needed for efficient gas exchange. The gravitational binding energy that holds our atmosphere to Earth is enormous, roughly equivalent to the energy output of the sun for several hours. This represents the amount of energy that would be required to completely strip away our atmosphere and disperse it into space. The fact that our atmosphere possesses this much gravitational binding energy demonstrates how securely it is held in place by Earth's gravitational field, making atmospheric escape virtually impossible under normal conditions. Gravity also helps protect our atmosphere from the solar wind, the stream of charged particles flowing outward from the sun that could potentially strip away atmospheric gases. By holding our atmosphere in a dense, compact configuration close to Earth's surface, gravity ensures that most of our atmospheric mass remains within the protective influence of Earth's magnetic field, which deflects most solar wind particles away from our planet. Picture how gravity shapes the very boundary between our atmosphere and space. Instead of creating a sharp, distinct boundary, gravity's gradually weakening influence allows our atmosphere to thin out slowly with altitude, creating a gradual transition zone where atmospheric gases become progressively more sparse until they merge almost imperceptibly with the vacuum of space. This graduated boundary, shaped by gravity's influence, helps prevent sudden atmospheric loss. The way gravity affects different atmospheric gases provides another example of its organizing influence. Heavier gases like carbon dioxide tend to settle toward lower altitudes where gravity's pull is stronger, while lighter gases like hydrogen and helium tend to rise toward higher altitudes where gravity's influence is weaker. This gravitational separation helps maintain atmospheric composition and prevents the lighter gases that might otherwise escape from becoming concentrated at dangerous levels. During your daily life, you experience gravity's atmospheric organization in countless subtle ways. The fact that you can breathe naturally at ground level, that weather patterns follow predictable cycles, that air pressure remains stable enough for comfortable living. All of these depend on gravity's role in organizing and maintaining atmospheric structure. Even the way sound travels through air, the way clouds form and move, and the way your body regulates internal pressure all depend on the gravitational organization of our atmosphere. The long-term stability of our atmosphere over geological timescales demonstrates gravity's effectiveness as an atmospheric organizing force. For billions of years, gravity has maintained our atmosphere's basic structure and composition despite volcanic eruptions, asteroid impacts, climate changes, and countless other disturbances. This gravitational stability has provided the consistent atmospheric environment necessary for life to evolve and flourish on Earth. Gravity's influence on atmospheric tides provides another fascinating example of its organizing role. Just as the moon and sun create tides in Earth's oceans, they also create subtle tidal effects in our atmosphere, causing slight variations in atmospheric pressure and density that follow predictable patterns. These atmospheric tides demonstrate how gravity continues to organize and influence our atmospheric system on multiple timescales. The gravitational potential energy stored in our atmosphere represents a vast reservoir of organized energy that helps maintain atmospheric stability. Air at higher altitudes possesses more gravitational potential energy than air at lower altitudes, and this energy gradient helps drive the circulation patterns and pressure dynamics that maintain atmospheric suspension. The conversion between gravitational potential energy and kinetic energy helps power many atmospheric processes. Consider how gravity's organizing influence extends beyond just holding our atmosphere in place to actually enabling the complex processes that make our planet habitable. The water cycle depends on gravity to bring precipitation back to Earth's surface, while also allowing evaporation and circulation patterns that distribute moisture throughout the atmosphere. Weather systems derive their energy partly from gravitational potential energy as air masses move between different altitudes. As you settle deeper into rest tonight, you can appreciate how gravity's gentle embrace creates a secure, stable environment for atmospheric suspension. Rather than fighting against atmospheric stability, gravity works in perfect cooperation with molecular motion, thermal energy, and pressure dynamics to create the complex but stable system that keeps our protective sky suspended above us. The gravitational field that holds our atmosphere also helps regulate its temperature through the process of adiabatic compression and expansion. As air moves to different altitudes within the gravitational field, It undergoes pressure changes that affect its temperature, helping to maintain the thermal gradients that drive atmospheric circulation and support atmospheric suspension. Gravity's role in atmospheric suspension represents one of nature's most elegant examples of how apparent opposites can work together to create stable, beneficial systems. The same force that pulls everything downward also enables the upward pressure and circulation that keep our atmosphere suspended, demonstrating how natural systems achieve stability through balance rather than dominance. Tonight, as you rest beneath our gravitationally organized atmosphere, you can sleep peacefully knowing that this fundamental force of nature continues its gentle, constant work of holding our protective sky in place, while allowing all the dynamic processes that maintain atmospheric suspension to operate freely and efficiently. Gravity's embrace is both secure and nurturing, providing the stability that makes atmospheric suspension possible while allowing the freedom of movement that keeps our sky alive and responsive to the changing needs of our living planet. Our planet breathes with a rhythm as steady and essential as your own quiet breathing tonight, moving vast masses of air and circulation patterns that span continents and oceans, rising from Earth's surface to the edge of space and back again in cycles that help maintain the atmospheric suspension we've been exploring. This planetary breathing, the global circulation of our atmosphere, represents one of the most beautiful and effective systems for maintaining atmospheric stability while distributing the energy and materials necessary for life. Picture Earth as a living organism with lungs that span entire hemispheres, inhaling solar energy and exhaling heat, drawing moisture from oceans and breathing it out as precipitation over land, lifting air from warm tropical regions and gently releasing it in cooler polar areas. This planetary respiration operates continuously, moving air masses weighing billions of tons with the same gentle efficiency that moves air through your own lungs as you rest peacefully tonight. The primary engine driving Earth's atmospheric breathing is the uneven heating of our planet's surface by solar radiation. The equatorial regions receive more intense sunlight throughout the year, while polar regions receive less direct solar energy, creating temperature differences that drive massive circulation patterns. Warm air near the equator rises like a gentle exhalation, creating low-pressure areas that draw in cooler air from surrounding regions, while cool air near the poles sinks like a deep inhalation, creating high-pressure areas that push air outward toward warmer regions. As you breathe slowly and naturally in your comfortable resting place, you can imagine similar processes occurring on a planetary scale around you. The warm air rising from sun-heated tropical oceans carries with it the energy and moisture that will eventually fall as rain in distant regions, while cool air flowing down from Arctic regions brings the temperature moderation that prevents our planet from becoming too hot in its sun-facing regions. This atmospheric circulation acts like a global air conditioning system, distributing heat and cooling where needed. The Coriolis effect, created by Earth's rotation, adds elegant complexity to our planet's breathing patterns. As air masses move across Earth's rotating surface, they curve gently to the right in the northern hemisphere and to the left in the southern hemisphere, creating the spiral patterns of high and low pressure systems that bring us our daily weather. This rotation-induced deflection helps organize atmospheric circulation into stable, predictable patterns that maintain atmospheric suspension while providing the weather variety that makes our planet interesting and habitable. Picture the way Earth's rotation creates these gentle spiral patterns in the moving air, like vast, invisible whirlpools that help organize atmospheric flow while preventing the kind of chaotic turbulence that might destabilize our atmospheric suspension. These rotating circulation patterns, cyclones and anticyclones, act like atmospheric gears, meshing together to create smooth, coordinated movement of air masses across the planet's surface and through its vertical atmospheric layers. The vertical circulation that carries air between Earth's surface and the upper atmosphere represents perhaps the most crucial aspect of planetary breathing for maintaining atmospheric suspension. Thermal updrafts and downdrafts create columns of moving air that transport energy, moisture, and atmospheric mass between different altitude levels, preventing any layer from becoming too dense or too light and maintaining the pressure gradients necessary for atmospheric stability. During daylight hours, solar heating creates thousands of thermal updrafts that lift warm air from Earth's surface toward higher altitudes. These rising air columns, invisible but powerful, carry thermal energy upward through the atmosphere while creating the convective circulation that helps support atmospheric weight. As warm air rises and cools, it eventually sinks back toward the surface, completing circulation loops that move atmospheric mass continuously throughout the vertical structure of our sky. Imagine these thermal circulation loops as invisible escalators running between Earth's surface and the upper atmosphere, constantly moving air up and down while distributing the thermal energy that maintains atmospheric suspension. Some of these circulation loops are small and local, lifting air from a sun-warmed parking lot or field, while others are enormous, moving air masses the size of entire states or countries through complex vertical journeys that may take days or weeks to complete. The seasonal variations in Earth's breathing patterns demonstrate the adaptive nature of atmospheric circulation. During summer months in each hemisphere, increased solar heating creates more vigorous circulation patterns, with stronger thermal updrafts and more active weather systems. During winter months, circulation becomes gentler but more stable, maintaining atmospheric suspension with less dramatic but equally effective air movement patterns. As seasons change in your part of the world, you experience the effects of these shifting planetary breathing patterns in the changing weather, the different cloud formations, and the varying intensity of wind patterns. Spring brings the awakening of more active circulation as solar heating increases, while autumn brings the calming of circulation patterns as heating decreases. These seasonal rhythm changes help maintain atmospheric stability while adapting to changing energy inputs from the sun. The interaction between ocean and atmospheric circulation creates some of the most important planetary breathing patterns. Warm ocean currents transfer heat from tropical regions toward polar areas, while cool ocean currents bring temperature moderation from polar regions toward the tropics. This oceanic circulation works together with atmospheric circulation to distribute thermal energy around the planet, maintaining the temperature gradients that drive atmospheric movement and suspension. Picture the way warm, moist air rises from tropical oceans, carrying water vapor high into the atmosphere, where it condenses into clouds and eventually falls as precipitation in distant regions. This process not only provides the fresh water necessary for life on land, but also helps maintain atmospheric circulation by releasing latent heat during condensation, providing additional energy to drive continued atmospheric movement and suspension. The jet streams that flow through the upper atmosphere represent some of the most dramatic examples of planetary breathing. These high-altitude rivers of fast-moving air circle the globe at altitudes where commercial aircraft fly, carrying weather systems across continents and helping to maintain the pressure patterns that support atmospheric suspension. The jet streams flow with remarkable consistency, moving at speeds that can exceed 200 miles per hour while maintaining stable patterns that help organize global atmospheric circulation. During your daily life, you experience the effects of these high-altitude air currents in the weather patterns they bring, the cloud formations they create, and even in the flight times of aircraft that either ride with or fight against these atmospheric rivers. The jet streams represent the upper level of planetary breathing, where the atmosphere moves with concentrated energy and purpose while maintaining the global circulation patterns that support atmospheric stability. The way mountains and other geographic features interact with planetary breathing patterns adds another layer of complexity to atmospheric circulation. Mountain ranges force air masses to rise, creating orographic lifting that enhances precipitation on windward slopes while creating rain shadows on leeward sides. These geographic influences on atmospheric circulation help create the diverse climate patterns that make different regions of our planet unique, while contributing to the overall stability of atmospheric suspension. Consider how the Rocky Mountains in North America or the Himalayas in Asia influence continental-scale breathing patterns, forcing air masses to rise and fall in ways that affect weather patterns across entire continents. These mountain-influenced circulation patterns help organize atmospheric flow while preventing the development of stagnant air masses that might threaten atmospheric stability. The daily cycle of heating and cooling creates its own rhythm in planetary breathing patterns. During daylight hours, solar heating enhances thermal circulation and creates more active atmospheric movement. During nighttime hours, radiative cooling reduces thermal circulation but allows atmospheric mass to redistribute and reorganize, maintaining circulation patterns on a more subtle but equally important level. As you rest during these nighttime hours, the planetary breathing patterns around you have shifted into their gentler nocturnal mode, with less dramatic thermal circulation but continued atmospheric movement that maintains the pressure patterns supporting atmospheric suspension. The atmosphere continues its essential circulation work even during the quiet hours, ensuring that atmospheric stability is maintained throughout the daily cycle. The global nature of atmospheric circulation means that air masses in your local region have traveled from distant parts of the planet, carrying with them the thermal energy and atmospheric characteristics of their origins. The air you're breathing tonight may have been part of Arctic circulation patterns, tropical thermal systems, or oceanic evaporation processes, demonstrating how planetary breathing connects all regions of Earth through atmospheric circulation. Pollution and other atmospheric constituents also participate in planetary breathing patterns, being carried around the world by circulation systems and demonstrating both the global connectivity of atmospheric circulation and the importance of maintaining healthy atmospheric composition. The same circulation patterns that maintain atmospheric suspension also distribute both beneficial and harmful atmospheric constituents, showing how planetary breathing affects environmental quality as well as atmospheric stability. The energy required to maintain Earth's breathing patterns comes primarily from solar radiation, but also includes geothermal energy from Earth's interior and kinetic energy from planetary rotation. This multi-source energy input helps ensure that planetary breathing patterns remain stable and consistent over long time periods, providing the reliable circulation necessary for sustained atmospheric suspension. Climate change affects planetary breathing patterns by altering the temperature gradients that drive circulation, potentially changing the intensity and distribution of atmospheric movement. Understanding these circulation patterns and their role in atmospheric suspension helps us appreciate both the stability and the sensitivity of our atmospheric system, highlighting the importance of maintaining the environmental conditions that support healthy planetary breathing. As you continue to breathe slowly and peacefully tonight, you're participating in a breathing rhythm that extends far beyond your individual respiratory needs to encompass the respiratory needs of our entire planet. Your breathing connects you to the global circulation patterns that maintain atmospheric suspension, making you a participant in the planetary breathing that keeps our sky stable and our atmosphere suspended in its protective embrace above the Earth. The beauty of planetary breathing lies in its self-regulating nature. Circulation patterns automatically adjust to changing conditions, maintaining atmospheric stability while adapting to variations in solar energy, seasonal changes, and other environmental factors. This automatic regulation ensures that our atmosphere continues to breathe steadily and effectively, maintaining the circulation patterns that support atmospheric suspension regardless of short-term variations in atmospheric conditions. Tonight, as Earth continues its ancient rhythm of atmospheric breathing around you, you can rest peacefully knowing that this planetary respiratory system will continue its essential work, moving air masses with gentle efficiency, distributing thermal energy with precise timing, and maintaining the circulation patterns that keep our protective atmosphere suspended stably above us throughout the night and far into the future. Above you as you rest tonight lies not simply a uniform ocean of air, but rather a beautifully organized vertical structure of distinct atmospheric layers, each with its own unique characteristics and essential role in maintaining the suspended stability of our planetary sky. These layers stack upon one another like invisible floors in an enormous aerial building, with each level supporting those above while being supported by those below, creating an architectural marvel of atmospheric engineering that has maintained its perfect structural integrity for billions of years. Picture yourself beginning a gentle upward journey through these atmospheric layers, starting from your comfortable resting place and rising slowly through each distinct region of our sky. As you ascend in this imagined journey, you would pass through zones where temperature, pressure, density, and atmospheric composition all change gradually but distinctly, creating the layered structure that distributes atmospheric weight efficiently while maintaining the circulation patterns that prevent our sky from ever collapsing under its own enormous mass. The first layer surrounding you right now is the troposphere, the lowest and most familiar region of our atmosphere, where all weather occurs and where you spend your entire life breathing and moving. This layer extends from Earth's surface up to about 6 to 10 miles above you, depending on your latitude and the season. The troposphere contains approximately 80% of our atmosphere's total mass, yet represents only a tiny fraction of the atmosphere's vertical extent, demonstrating how efficiently the lower atmospheric layers organize and compress atmospheric weight. As you breathe slowly and peacefully in this moment, you're experiencing the troposphere at its most dense and supportive level. The air around you contains the highest concentration of oxygen and other gases necessary for life, while the pressure created by all the atmospheric layers above provides the perfect environment for comfortable breathing and circulation within your body. The troposphere's density and pressure create the foundation that supports all the atmospheric layers above, like a strong first floor that bears the weight of an entire building. The temperature structure of the troposphere plays a crucial role in maintaining atmospheric suspension. Generally, temperature decreases with altitude throughout this layer, creating the thermal gradients that drive the convective circulation we explored earlier. This temperature decrease occurs because the troposphere is heated primarily from below by Earth's surface rather than directly from above by solar radiation, creating the thermal instability that generates the rising and sinking air motions essential for atmospheric circulation. Picture the countless thermal circulation cells operating within the troposphere around you right now, invisible columns of air rising from warm surfaces and sinking from cooler regions, creating a complex three-dimensional network of circulation that moves atmospheric mass continuously throughout this lowest layer. This constant circulation prevents the troposphere from settling into static layers that might become unstable, instead maintaining the dynamic pressure distribution that supports the atmospheric layers above. The boundary between the troposphere and the next atmospheric layer above, called the tropopause, represents one of nature's most remarkable atmospheric engineering achievements. At this boundary, the temperature structure of the atmosphere changes dramatically, shifting from the decreasing temperatures of the troposphere to the increasing temperatures of the stratosphere above. This temperature inversion creates a stable barrier that helps contain weather activity within the troposphere, while supporting the distinctly different atmospheric processes of higher layers. Imagine this tropopause boundary as an invisible ceiling that helps organize atmospheric structure while allowing essential vertical exchanges between layers. The temperature inversion at the tropopause acts like an atmospheric floor that supports the stratosphere above, while containing most vertical air motion within the troposphere below. This layered organization helps maintain atmospheric stability by preventing excessive mixing between atmospheric regions with different pressure, temperature, and composition characteristics. Above the tropopause lies the stratosphere, extending from about 10 miles to approximately 30 miles above Earth's surface. This layer contains the famous ozone layer that protects us from harmful solar ultraviolet radiation. But from the perspective of atmospheric suspension, the stratosphere serves as a crucial middle layer that helps distribute atmospheric weight while maintaining the thermal structure necessary for global atmospheric stability. The stratosphere's unique temperature profile, with temperatures that actually increase with altitude due to solar heating of the ozone layer, creates atmospheric conditions that support remarkably stable circulation patterns. Unlike the turbulent convective activity of the troposphere, the stratosphere moves in large, stable circulation patterns that change slowly and predictably, providing atmospheric stability that supports both the turbulent troposphere below and the even more rarefied atmospheric layers above. Picture the stratosphere as a vast, calm reservoir of atmospheric mass that provides stability and continuity to our atmospheric structure. While the troposphere churns with daily weather activity and the upper atmospheric layers respond quickly to solar and magnetic influences, the stratosphere maintains steady, reliable circulation patterns that help buffer atmospheric changes and maintain overall stability in our sky's suspended structure. The mesosphere, extending from about 30 to 50 miles above Earth's surface, represents the middle atmospheric layer where atmospheric density becomes quite low but still sufficient to create the meteor phenomena we sometimes see as shooting stars. This layer plays an important role in atmospheric suspension by providing a transition zone between the denser lower layers and the extremely thin upper layers, helping to distribute atmospheric weight gradually across a greater vertical range. In the mesosphere, atmospheric temperature again decreases with altitude, reaching the coldest temperatures found anywhere in Earth's atmosphere. These cold temperatures create unique circulation patterns that help maintain atmospheric structure while processing the small amounts of meteoric material that enter our atmosphere from space. The mesosphere circulation patterns help maintain atmospheric stability by providing another layer of organized atmospheric motion that supports the overall suspended structure of our sky. Picture the mesosphere as an atmospheric buffer zone that helps prevent sudden transitions between the relatively dense lower atmosphere and the extremely thin upper atmosphere. This gradual transition in atmospheric properties helps maintain structural stability while allowing the complex circulation patterns of different atmospheric layers to operate without interfering destructively with each other. Above the mesosphere lies the thermosphere, where atmospheric density becomes extremely low, but temperatures can reach surprisingly high levels due to absorption of high-energy solar radiation. Although the thermosphere contains very little atmospheric mass compared to lower layers, it plays an important role in atmospheric suspension by providing the outermost structural boundary of our atmosphere and helping to process the energetic solar radiation that could otherwise disrupt lower atmospheric layers. The thermosphere's high temperatures might seem contradictory to our understanding of cold outer space, but these temperatures result from the high-energy solar radiation that strikes the sparse atmospheric molecules in this region. Each molecule absorbs enormous amounts of energy, creating high kinetic temperatures even though the overall thermal energy content remains low due to the extremely low atmospheric density. Imagine the thermosphere as the outermost protective layer of our atmospheric structure, absorbing and processing the most energetic solar radiation before it can reach the denser atmospheric layers below. This outermost layer helps maintain atmospheric suspension by preventing energetic solar radiation from disrupting the pressure and circulation patterns of the lower atmospheric layers that contain most of our atmosphere's mass. The way these atmospheric layers interact and support each other creates a remarkably stable and efficient system for maintaining atmospheric suspension. Each layer contributes its own specialized function to overall atmospheric stability while depending on the other layers for structural support and circulation connectivity. The troposphere provides the dense foundation and active circulation. The stratosphere provides stable middle layer organization. The mesosphere provides transitional buffering, and the thermosphere provides outer boundary protection. Consider how pressure changes smoothly but continuously as you move between these atmospheric layers, creating pressure gradients that support atmospheric suspension while maintaining the distinct characteristics that make each layer unique. The pressure differences between layers drive interlayer circulation that helps maintain atmospheric unity while preserving layer-specific properties, creating both diversity and coherence in atmospheric structure. The seasonal variations that affect each atmospheric layer demonstrate the adaptive nature of our layered atmospheric system. Changes in solar heating create seasonal pressure and temperature variations within each layer, but the overall layered structure remains stable because each layer responds to seasonal changes in ways that maintain rather than disrupt overall atmospheric suspension. During winter months in your hemisphere, Each atmospheric layer adjusts its circulation patterns and thermal structure to accommodate reduced solar heating. But these adjustments occur in coordinated ways that maintain overall atmospheric stability. The layered structure provides both flexibility and stability, allowing seasonal adaptation while preserving the fundamental atmospheric architecture that keeps our sky suspended. The vertical mixing that occurs between atmospheric layers helps maintain atmospheric composition and energy distribution while preserving the distinct characteristics that make each layer functionally unique. This selective mixing allows essential atmospheric constituents to move between layers when necessary, while preventing the kind of homogenization that would eliminate the beneficial layer-specific properties that contribute to atmospheric suspension. Picture the gentle exchange processes that occur at layer boundaries, allowing atmospheric constituents and energy to move between layers in carefully regulated amounts that maintain both layer identity and overall atmospheric unity. These exchange processes operate continuously but gradually, maintaining atmospheric stability while allowing the dynamic responses necessary for a living, adaptive atmospheric system. The ozone layer within the stratosphere provides an excellent example of how layer-specific properties contribute to overall atmospheric suspension. By absorbing ultraviolet solar radiation, the ozone layer not only protects life on Earth's surface, but also creates the thermal heating that maintains stratospheric temperature structure and circulation patterns. This demonstrates how atmospheric chemistry and atmospheric physics work together to maintain atmospheric suspension. The research conducted by atmospheric scientists using weather balloons, satellite measurements, and other tools has revealed the detailed structure and behavior of these atmospheric layers, confirming the remarkable stability and efficiency of our layered atmospheric system. This scientific understanding helps us appreciate the sophisticated natural engineering that maintains atmospheric suspension while adapting to changing environmental conditions. As you rest tonight beneath this magnificent layered atmospheric structure, you can appreciate how each layer contributes its specialized function to the overall stability that keeps our sky suspended above us. The troposphere surrounds you with its dense, life-supporting atmosphere, while the stratosphere, mesosphere, and thermosphere extend above in their carefully organized sequence, each playing its essential role in maintaining the atmospheric architecture that has protected and sustained life on Earth for billions of years. The beauty of our layered atmospheric system lies in its combination of stability and adaptability. Each layer maintains its essential characteristics and functions while adjusting continuously to changing conditions, creating an atmospheric structure that remains fundamentally stable while staying dynamically responsive to the changing needs of our living planet. Tonight, as you drift toward deeper rest, these atmospheric layers continue their ancient work of organizing and maintaining the suspended structure of our sky, each layer supporting those above and being supported by those below in an invisible architectural marvel that demonstrates the elegant efficiency of natural atmospheric engineering. Surrounding our planet like an invisible protective bubble, Earth's magnetic field extends far beyond our atmosphere into space, creating a magnetosphere that plays a crucial but often overlooked role in maintaining atmospheric suspension by shielding our air from the constant stream of charged particles flowing outward from the sun. This magnetic protection prevents the gradual erosion of our atmosphere that would otherwise occur over geological time, helping to preserve the atmospheric mass and pressure that keep our sky suspended in stable configuration above Earth's surface. Picture this magnetic field as an enormous, invisible umbrella that deflects most of the solar wind, a continuous flow of electrically charged particles streaming away from the sun at speeds of several hundred miles per second. Without this magnetic protection, these energetic particles would gradually strip away our atmosphere molecule by molecule, eventually leaving Earth as airless as Mars, which lost much of its atmosphere partly due to its weak magnetic field and inadequate protection from solar wind erosion. As you rest comfortably tonight, you exist within the protective embrace of this magnetic shield, completely unaware of the invisible deflection of potentially harmful solar particles that occurs continuously high above our atmosphere. The magnetic field lines that surround Earth curve gracefully from the magnetic South Pole to the magnetic North Pole, creating pathways that guide charged solar particles around our planet rather than allowing them to impact our atmosphere directly. The magnetosphere extends approximately 40,000 miles in a space on the side facing the Sun and stretches even farther on the night side of Earth, creating an elongated protective cavity within the solar wind. This cavity, called the magnetospheric cavity, contains our entire atmosphere within its protective boundaries, ensuring that atmospheric molecules remain safely within Earth's gravitational and magnetic influence rather than being swept away by solar wind pressure. The interaction between Earth's magnetic field and the solar wind creates one of the most beautiful and dynamic boundaries in our solar system. At the magnetopause, where Earth's magnetic field meets the solar wind, the pressure from flowing solar particles compresses our magnetic field on the day side, while stretching it into a long magnetic tail on the night side. This constantly shifting boundary demonstrates the active, dynamic nature of magnetic protection while maintaining overall stability that preserves atmospheric integrity. Picture the way this magnetic boundary flexes and adjusts in response to variations in solar wind pressure, much like a soap bubble maintaining its integrity while being gently blown by varying air currents. The magnetosphere's ability to maintain its protective function despite constant pressure variations demonstrates the robust nature of magnetic atmospheric protection, while showing how natural systems maintain stability through dynamic adaptation rather than rigid resistance. During periods of intense solar activity, when the Sun releases particularly energetic bursts of charged particles called solar storms or coronal mass ejections, our magnetic field provides enhanced protection that prevents these energetic events from disrupting atmospheric stability. The magnetic field lines compress and strengthen under increased solar wind pressure, creating stronger deflection that maintains atmospheric protection even during extreme space weather conditions. The aurora phenomena that occur near Earth's polar regions provide visible evidence of our magnetic field's protective work. When some solar wind particles do manage to penetrate the magnetosphere, they follow magnetic field lines toward the polar regions where they interact with atmospheric gases to create the beautiful curtains of light we call the northern and southern lights. These auroral displays demonstrate that our magnetic protection is active and effective, while showing how the small amounts of solar particles that do reach our atmosphere are safely channeled to regions where they create beauty rather than atmospheric damage. As you settle deeper into rest tonight, you can appreciate how the aurora represents a visible sign of invisible protection, showing how our magnetic field guides potentially harmful solar particles into harmless and beautiful interactions with the outermost reaches of our atmosphere. The fact that auroral activity occurs primarily in polar regions demonstrates how effectively the magnetic field protects the vast majority of our atmosphere from direct solar wind impact. The Earth's magnetic field is generated deep within our planet's core, where the motion of molten iron creates electrical currents that produce the magnetic field lines extending into space. This geodynamo process has operated continuously for billions of years, providing the persistent magnetic protection necessary for long-term atmospheric preservation. The stability and longevity of this magnetic generation process helps ensure that atmospheric protection will continue far into the future. The strength of Earth's magnetic field, while varying slightly over time, remains sufficient to provide effective atmospheric protection under normal solar conditions. The magnetic field strength is measured in units called Gauss, and Earth's surface magnetic field strength of approximately half a Gauss provides adequate deflection of solar wind particles while being gentle enough to avoid interfering with biological processes or atmospheric circulation patterns. Consider how different our planet might be without this magnetic protection. Mars, which is only a weak remnant magnetic field, has lost much of its original atmosphere to solar wind erosion over geological time. Venus, despite having a thick atmosphere, lacks a strong magnetic field and experiences atmospheric loss processes that our magnetic protection prevents. Earth's combination of adequate magnetic field strength and gravitational attraction creates optimal conditions for long-term atmospheric preservation. The way Earth's magnetic field interacts with atmospheric ions demonstrates another aspect of magnetic atmospheric protection. The ionosphere, the electrically charged upper portion of our atmosphere, is influenced by magnetic field lines that help organize and contain charged atmospheric particles. This magnetic organization of ionospheric structure contributes to atmospheric stability while enabling the radio communication and navigation systems that depend on ionospheric properties. During your daily life, you benefit from magnetic protection in ways that extend beyond atmosphere preservation. The magnetic field that protects our atmosphere also shields the surface from harmful cosmic radiation that could otherwise pose health risks to life on Earth. This radiation protection works together with atmospheric shielding to create multiple layers of protection that maintain the safe, stable environment necessary for life to flourish. The solar wind pressure that our magnetic field deflects varies with the 11-year solar cycle, creating long-term variations in the strength and configuration of our magnetospheric protection. During solar maximum periods, increased solar activity creates stronger solar wind pressure that compresses our magnetosphere, while during solar minimum periods, reduced solar activity allows our magnetic field to expand further into space. These cyclical variations demonstrate the adaptive nature of magnetic protection, while showing how natural systems maintain long-term stability despite periodic changes. The magnetic field lines that protect our atmosphere also guide the circulation of charged particles within the magnetosphere, creating radiation belts called the Van Allen belts that trap and contain energetic particles at safe distances from Earth's surface and atmosphere. These radiation belts act like magnetic storage containers that prevent harmful particles from reaching our atmosphere, while demonstrating the sophisticated organization that magnetic fields create in space environments. Picture the Van Allen radiation belts as invisible magnetic containers circling high above our atmosphere, safely holding energetic particles that could otherwise pose threats to atmospheric stability or surface life. The magnetic field lines that create these belts demonstrate how magnetic organization extends far beyond simple deflection to include complex particle management that enhances overall atmospheric protection. The interaction between Earth's magnetic field and the interplanetary magnetic field carried by the solar wind creates additional complexity in magnetospheric protection. When the interplanetary magnetic field aligns favorably with Earth's magnetic field, protection is enhanced, while unfavorable alignment can create conditions where more solar wind particles penetrate the magnetosphere. These magnetic field interactions show how space weather affects atmospheric protection while demonstrating the overall effectiveness of magnetic shielding. The magnetic storms that occasionally occur when Earth's magnetosphere is disturbed by intense solar activity provide examples of how our magnetic protection system responds to extreme conditions. During magnetic storms, increased energy input from solar wind interactions can create enhanced auroral activity and temporary disruptions to radio communications. But atmospheric protection remains effective, and atmospheric loss does not occur even during the most intense magnetic disturbances. As technology has advanced, scientists have developed increasingly sophisticated methods for monitoring and studying Earth's magnetosphere, including satellite missions that measure magnetic field strength and solar wind conditions throughout the region surrounding our planet. This research has confirmed the crucial role of magnetic protection in maintaining atmospheric stability while revealing the complex and dynamic nature of magnetospheric processes. The comparison between Earth's magnetic protection and the magnetic environments of other planets helps us appreciate the optimal nature of our magnetospheric shielding. Jupiter's enormous magnetic field creates radiation environments too intense for life as we know it, while Mercury's weak magnetic field provides insufficient protection for atmospheric retention. Earth's magnetic field represents a perfect balance that provides adequate protection without creating harmful effects. Climate change and atmospheric research have shown that while human activities can affect atmospheric composition and circulation patterns, The fundamental magnetic protection that preserves atmospheric mass operates on much longer timescales and remains stable despite short-term atmospheric changes. This magnetic stability provides confidence that atmospheric preservation will continue regardless of temporary climate variations. The role of magnetic protection in atmospheric suspension demonstrates how multiple natural systems work together to maintain atmospheric stability. Gravitational attraction holds our atmosphere close to Earth. Molecular motion creates the pressure that supports atmospheric weight. Circulation patterns distribute atmospheric mass and energy. Atmospheric layers organize vertical structure, and magnetic fields protect against external erosion, all working together to maintain the suspended stability of our sky. Tonight, as you rest peacefully beneath our magnetically protected atmosphere, you can sleep securely knowing that this invisible shield continues its vigilant work, deflecting harmful solar particles, preserving atmospheric mass, and maintaining the protective conditions that have sheltered life on Earth for billions of years. The magnetic field that surrounds our planet operates silently and continuously, providing protection you never have to think about while ensuring that our atmosphere remains safely suspended in its protective embrace around our living world. The beauty of magnetic atmosphere protection lies in its invisible effectiveness. You never see it working, never feel its influence directly, never need to worry about its function. Yet it operates with perfect reliability to maintain the atmospheric conditions that make life possible. This magnetic shield represents one of nature's most elegant solutions to the challenge of preserving atmospheric stability in the dynamic environment of interplanetary space. The thermal energy that flows through our atmosphere, like an invisible river of warmth, performs the quiet but essential work of maintaining atmospheric suspension through processes so fundamental and continuous that we rarely consider their crucial importance. Temperature differences create the pressure variations that drive circulation, while thermal energy provides the molecular motion that prevents gravitational collapse, making heat and thermal dynamics perhaps the most vital but overlooked factor in keeping our massive sky suspended safely above Earth's surface. Picture thermal energy as the lifeblood of our atmospheric system, flowing from the sun to Earth's surface, rising through atmospheric layers, spreading horizontally across continents and oceans, and eventually radiating back to space, creating during its journey through our atmosphere all the thermal gradients and energy distributions that maintain atmospheric suspension. This constant flow of thermal energy, measured in quantities so vast they dwarf human energy consumption, operates with the gentle efficiency that characterizes all natural atmospheric processes. As you rest comfortably tonight, your body is surrounded by air that contains thermal energy equivalent to the motion of trillions of molecules bouncing against each other at speeds that approach the speed of sound. This thermal energy, invisible and unfelt except as the comfortable temperature that allows restful sleep, represents the kinetic energy of molecular motion that creates atmospheric pressure and prevents our sky from collapsing under the weight of gravity. The sun provides virtually all the thermal energy that drives atmospheric suspension, delivering approximately 174,000 terawatts of energy to Earth's atmosphere and surface, an amount of energy so enormous that it exceeds total human energy consumption by a factor of more than 10,000. This solar energy input arrives at Earth's atmosphere as electromagnetic radiation, where it begins its complex journey of absorption, reflection, conversion, and redistribution that maintains the thermal conditions necessary for atmospheric stability. When solar radiation reaches our atmosphere, different wavelengths of light interact with atmospheric gases in different ways, creating the selective heating that establishes thermal gradients throughout atmospheric layers. Shorter wavelengths, including ultraviolet radiation, are absorbed by gases in the upper atmosphere, heating the thermosphere and stratosphere, while longer wavelengths pass through to heat Earth's surface, which then warms the troposphere from below through conduction and convection. Picture this solar energy absorption as a sophisticated heating system that warms different parts of our atmosphere at different rates and in different ways, creating the temperature differences that drive the circulation patterns essential for atmospheric suspension. Unlike artificial heating systems that might create hotspots or uneven heating, solar heating operates through natural processes that distribute thermal energy gradually and efficiently throughout our entire atmospheric system. The way Earth's surface absorbs and re-radiates solar energy creates the fundamental thermal engine that drives atmospheric circulation and maintains suspension. During daylight hours, solar heating warms land and ocean surfaces, which then heat the air above them through conduction and evaporation. This surface heating creates thermal updrafts that lift warm air toward higher altitudes while drawing cooler air inward to replace the rising air, generating convective circulation that helps support atmospheric weight. As darkness falls in your part of the world tonight, the direct solar heating of your local region has ceased, but the thermal energy stored in land masses, ocean waters, and atmospheric air continues to drive circulation patterns that maintain atmospheric suspension. The thermal inertia of these natural heat reservoirs ensures that atmospheric circulation continues throughout the night, maintaining the pressure patterns that support our sky even when immediate solar energy input is reduced. The temperature gradients that exist throughout our atmosphere create the pressure differences that drive both vertical and horizontal air movement, with warm air rising due to its lower density and cool air sinking due to its higher density. These thermally driven pressure differences generate the atmospheric circulation that prevents stagnation and maintains the dynamic pressure distribution necessary for atmospheric suspension. Without thermal energy to create these temperature differences, our atmosphere would lack the circulation necessary for stable suspension. Consider how the thermal properties of different atmospheric gases contribute to overall atmospheric stability. Water vapor, carbon dioxide, and other greenhouse gases absorb and re-radiate thermal energy in ways that help maintain atmospheric temperature gradients, while nitrogen and oxygen, the primary atmospheric gases, store and transport thermal energy through convective circulation. This thermal behavior of atmospheric gases creates the heat distribution patterns that support atmospheric suspension. The daily cycle of heating and cooling that results from Earth's rotation creates rhythmic thermal patterns that help organize atmospheric circulation while maintaining overall stability. During daylight hours, increased thermal energy enhances circulation and atmospheric activity, while during nighttime hours, reduced heating allows thermal energy redistribution and the continuation of circulation patterns established during daylight. This daily thermal rhythm helps maintain atmospheric suspension through both active and quiet periods. Picture the way thermal energy moves through the atmosphere like slow, invisible waves, spreading from regions of intense solar heating toward cooler regions, creating the thermal circulation that distributes atmospheric mass and maintains pressure equilibrium. These thermal waves operate on multiple time scales, from the rapid circulation of convective cells that develop within hours, to seasonal thermal patterns that develop over months, to climate-scale thermal circulation that operates over years and decades. The seasonal variations in solar heating that result from Earth's tilted axis create longer-term thermal patterns that help maintain atmospheric stability while allowing adaptive responses to changing energy inputs. During summer months in each hemisphere, increased solar heating enhances atmospheric circulation and creates more vigorous thermal activity. During winter months, reduced heating creates gentler circulation patterns that maintain atmospheric suspension with less thermal energy input. The thermal energy stored in Earth's oceans plays a crucial role in maintaining atmospheric temperature stability and circulation patterns. Ocean water has a much higher heat capacity than air, allowing oceans to store enormous amounts of thermal energy that moderates atmospheric temperature changes and provides thermal energy for atmospheric circulation long after direct solar heating has ceased. This oceanic thermal storage helps maintain atmospheric suspension by providing consistent thermal energy input to atmospheric circulation. Imagine the world's oceans as vast thermal batteries that collect and store solar energy during periods of intense heating. Then slowly release this stored thermal energy to maintain atmospheric circulation during periods of reduced solar input. Ocean currents transport thermal energy around the planet, creating thermal gradients that drive atmospheric circulation while providing the thermal stability that maintains consistent atmospheric suspension despite variations in solar energy input. The process of evaporation and condensation represents one of the most important thermal mechanisms for maintaining atmospheric suspension. When water evaporates from ocean and land surfaces, it absorbs latent heat energy that becomes stored in atmospheric water vapor. When this water vapor condenses to form clouds and precipitation, the stored latent heat is released, providing thermal energy that drives atmospheric circulation and helps maintain the convective activity essential for atmospheric suspension. Picture the water cycle as a massive thermal engine that transports energy from Earth's surface high into the atmosphere through evaporation, then releases this energy at higher altitudes through condensation, creating thermal circulation that helps support atmospheric weight while distributing thermal energy throughout the vertical structure of our sky. This evaporation-condensation thermal engine operates continuously, providing reliable thermal input to atmospheric circulation systems. The greenhouse effect, created by atmospheric gases that absorb and re-radiate thermal radiation, helps maintain the thermal energy necessary for atmospheric suspension by preventing excessive loss of thermal energy to space. Without greenhouse gases to moderate thermal radiation, Earth's surface and atmosphere would lose thermal energy so rapidly that atmospheric circulation would be insufficient to maintain stable suspension. The natural greenhouse effect provides thermal regulation that maintains optimal conditions for atmospheric stability. The thermal radiation that Earth emits back to space represents the ultimate destination of solar thermal energy after it has performed its essential work of maintaining atmospheric circulation and suspension. This outgoing thermal radiation must balance incoming solar radiation to maintain thermal equilibrium. But the thermal energy performs crucial atmospheric work during its journey from absorption to emission, creating the thermal circulation that keeps our sky suspended. Consider how thermal energy creates the convective stability that prevents atmospheric layers from developing dangerous temperature inversions or stagnant conditions that might threaten atmospheric suspension. Thermal circulation continuously mixes atmospheric layers, preventing the development of sharp thermal boundaries that might create atmospheric instabilities. This thermal mixing maintains the gradual temperature transitions that support stable atmospheric layering. The way thermal energy interacts with atmospheric chemistry demonstrates another aspect of temperature's role in atmospheric suspension. Chemical reactions within the atmosphere, including the formation and destruction of ozone and other atmospheric constituents, depend on thermal energy to proceed at rates that maintain atmospheric composition and the chemical processes that support atmospheric stability. Thermal expansion and contraction of atmospheric gases in response to temperature changes helps maintain atmospheric suspension by creating the density variations that drive circulation while preventing excessive compression or expansion that might destabilize atmospheric structure. The thermal properties of atmospheric gases ensure that temperature changes create beneficial circulation rather than harmful instabilities. During extreme weather events, thermal energy redistribution demonstrates the atmosphere's ability to maintain suspension even under unusual thermal conditions. Hurricanes, thunderstorms, and other intense weather systems represent concentrations of thermal energy that, while dramatic locally, help distribute thermal energy and maintain overall atmospheric circulation patterns that support atmospheric suspension. The research conducted by atmospheric scientists using satellite temperature measurements, weather balloon data, and climate monitoring systems has revealed the detailed thermal structure and behavior of our atmosphere, confirming the crucial role of thermal energy in maintaining atmospheric suspension while revealing the sophisticated thermal regulation that operates throughout our atmospheric system. As you continue to rest peacefully tonight, thermal energy continues its quiet work around you, maintaining the molecular motion that creates atmospheric pressure, driving the circulation that prevents atmospheric stagnation, and regulating the temperature gradients that support atmospheric layering. The thermal processes that maintain atmospheric suspension operate with such reliability and efficiency that you never need to think about them. Yet they provide the essential energy that keeps our protective sky suspended safely above our living world. The beauty of thermal atmospheric maintenance lies in its gentle, continuous operation. Thermal energy flows through our atmosphere like a life-giving circulation system, maintaining the conditions necessary for atmospheric suspension while creating the comfortable thermal environment that supports life on Earth. This thermal circulation represents one of nature's most elegant solutions to the challenge of maintaining atmospheric stability in a dynamic thermal environment. Tonight, as thermal energy continues its ancient work of maintaining atmospheric suspension, you can rest securely knowing that these thermal processes will continue their essential circulation throughout the night and far into the future, providing the thermal foundation that keeps our magnificent sky suspended in its protective embrace above our planet's surface. Within our suspended atmosphere flows an endless cycle of water that connects every level of our sky from the surface where you rest to the highest clouds, creating one of the most beautiful and essential systems for maintaining atmospheric suspension through the continuous circulation of moisture, energy, and atmospheric mass. This water cycle operates as a vast atmospheric engine that lifts billions of tons of water vapor from Earth's surface high into the atmosphere, then gently returns it as precipitation, creating during this endless journey the circulation patterns and energy transport that help keep our sky suspended in stable equilibrium. Picture this water cycle as nature's most elegant perpetual motion machine, powered by solar energy and driven by the same atmospheric processes that maintain suspension, moving water molecules through an endless journey from ocean to atmosphere to land and back again. Each water molecule that participates in this cycle carries with it thermal energy and contributes to atmospheric circulation, making the water cycle both a consequence of atmospheric suspension and a vital mechanism for maintaining it. As you breathe slowly and peacefully tonight, you're participating in this endless water cycle, exhaling water vapor that adds to the atmospheric moisture content while inhaling air that contains water molecules that may have traveled across oceans, through clouds, fallen as rain or snow, flowed through rivers, and evaporated again countless times in their atmospheric journey. The water vapor in each breath connects you directly to the global circulation system that maintains atmospheric suspension. The evaporation process that lifts water from Earth's surface into the atmosphere represents one of the most important mechanisms for transporting energy and maintaining atmospheric circulation. When solar energy converts liquid water into water vapor, it stores latent heat energy in the vapor molecules, effectively moving thermal energy from Earth's surface up into the atmosphere, where it can drive circulation patterns. This energy transport helps maintain the thermal gradients necessary for atmospheric suspension while creating the convective activity that prevents atmospheric stagnation. Consider the enormous scale of atmospheric water transport. Approximately 125 trillion gallons of water evaporate into our atmosphere every day, carrying with them thermal energy equivalent to the explosion of millions of atomic bombs. Yet this massive energy transport occurs so gently and gradually that you experience it only as comfortable humidity levels and a pleasant sensation of moisture in the air around you as you rest tonight. Picture the invisible rising of water vapor from every water surface on Earth, from vast oceans that stretch beyond the horizon, from lakes and rivers that reflect the sky, from moist soil and vegetation that transpire water through their leaves, from your own skin as your body regulates temperature through perspiration. This continuous evaporation creates countless invisible columns of rising moist air that help support atmospheric weight while transporting energy upward through atmospheric layers. The condensation process that creates clouds demonstrates the water cycle's role in maintaining atmospheric circulation and supporting atmospheric suspension. When water vapor rises high enough to reach cooler atmospheric temperatures, it condenses into tiny droplets that form clouds, releasing the latent heat energy that was stored during evaporation. This heat release in the upper atmosphere helps drive continued atmospheric circulation while creating the cloud systems that participate in atmospheric dynamics. Imagine clouds as visible evidence of the water cycle's atmospheric work. floating demonstrations of how water vapor carries energy from Earth's surface to higher atmospheric levels, where it supports circulation patterns essential for atmospheric suspension. The fact that clouds can float at various altitudes throughout the atmosphere shows how the water cycle helps maintain atmospheric structure while creating the weather patterns that distribute atmospheric mass and energy. The precipitation process that brings water back to Earth's surface completes the atmospheric portion of the water cycle, while contributing to atmospheric circulation through the vertical movement of air masses that accompanies weather systems. Rain, snow, and other forms of precipitation represent the return portion of the water cycle's atmospheric journey, bringing water molecules back to Earth's surface where they can begin the cycle again while participating in the circulation patterns that maintain atmospheric suspension. Picture the gentle falling of precipitation as nature's way of maintaining atmospheric circulation balance, with a downward movement of water droplets helping to organize air circulation patterns while redistributing atmospheric mass and energy. The fact that precipitation falls gently rather than all at once demonstrates the water cycle's role in maintaining atmospheric stability rather than creating disturbances that might threaten suspension. The horizontal transport of water vapor by atmospheric circulation creates one of the most important mechanisms for distributing moisture and maintaining atmospheric balance across different regions of our planet. Water that evaporates from tropical oceans may travel thousands of miles through atmospheric circulation before condensing and falling as precipitation in distant regions, demonstrating how the water cycle helps maintain global atmospheric circulation while distributing both moisture and energy. As you rest tonight, atmospheric circulation may be carrying water vapor from distant oceans across continents and mountain ranges, transporting not only moisture, but also the thermal energy that helps maintain circulation patterns. This long-distance atmospheric transport demonstrates how the water cycle connects all regions of our planet through atmospheric circulation while contributing to the global patterns that maintain atmospheric suspension. The seasonal variations in the water cycle help maintain atmospheric suspension through changing conditions while demonstrating the adaptive nature of atmospheric circulation systems. During warm seasons, increased evaporation enhances atmospheric circulation and energy transport, while during cool seasons, reduced evaporation creates gentler circulation patterns that maintain atmospheric stability with different moisture and energy distributions. Consider how the water cycle adapts to seasonal changes in solar energy input while maintaining its essential role in atmospheric circulation. Spring brings increased evaporation as warming temperatures enhance the water cycle's energy transport. Summer brings peak water cycle activity that supports maximum atmospheric circulation. Autumn brings gradual reduction in water cycle intensity. And winter brings minimal but continued water cycle activity that maintains atmospheric circulation through reduced energy conditions. The interaction between the water cycle and atmospheric pressure systems demonstrates the intimate connection between moisture circulation and atmospheric suspension. High-pressure systems typically bring clear skies and reduced precipitation, representing regions where atmospheric circulation creates stable conditions, while low-pressure systems bring clouds and precipitation, representing regions where atmospheric circulation creates rising air motion that supports atmospheric weight distribution. Picture atmospheric pressure systems as organizing mechanisms for the water cycle, with high-pressure areas serving as regions where atmospheric circulation gathers and concentrates atmospheric mass, while low-pressure areas serve as regions where atmospheric circulation lifts and redistributes atmospheric mass. The water cycle responds to these pressure patterns while helping to maintain them through latent heat transport and energy redistribution. The vertical transport of moisture through atmospheric layers demonstrates the water cycle's role in maintaining atmospheric structure and preventing layer stagnation. Water vapor that evaporates at Earth's surface can reach the highest levels of the troposphere, carrying energy and contributing to circulation that maintains connection between atmospheric layers while preventing the development of stagnant zones that might threaten atmospheric stability. The role of vegetation in the water cycle adds biological complexity to atmospheric moisture circulation while demonstrating how life on Earth participates in maintaining atmospheric suspension. Trees and other plants transpire enormous quantities of water vapor into the atmosphere, contributing to atmospheric moisture content while creating local circulation patterns that support regional atmospheric stability. Imagine forests as living components of the atmospheric circulation system, breathing out water vapor that rises into the atmosphere while breathing in carbon dioxide that participates in atmospheric chemistry. This biological participation in the water cycle demonstrates how life on Earth contributes to maintaining the atmospheric conditions that support continued life, creating beneficial feedback loops that enhance atmospheric stability. The purification process that occurs during the water cycle helps maintain atmospheric chemistry while demonstrating the cycle's role in atmospheric maintenance. As water evaporates, it leaves behind dissolved substances, becoming pure water vapor that helps maintain atmospheric composition. When this pure water vapor condenses and falls as precipitation, it provides fresh water for terrestrial life, while completing the purification process that maintains both atmospheric and surface water quality. The energy balance of the water cycle represents a crucial component of the overall energy balance that maintains atmospheric suspension. The energy required for evaporation must be balanced by the energy released during condensation, creating energy circulation patterns that help maintain atmospheric thermal balance, while driving the circulation necessary for atmospheric suspension. Consider how the water cycle serves as both a consequence and a cause of atmospheric circulation. Circulation patterns drive water cycle activity by transporting moisture and creating temperature gradients for evaporation and condensation, while water cycle activity drives circulation patterns by transporting energy and creating pressure differences through evaporation and condensation processes. The timescales of the water cycle demonstrate its role in both short-term atmospheric maintenance and long-term atmospheric stability. Individual water molecules may complete the atmospheric portion of their journey in days or weeks, while the overall water cycle operates continuously over geological timescales, providing both immediate circulation support and long-term atmospheric maintenance. The research conducted by atmospheric scientists using satellite measurements of atmospheric moisture, precipitation monitoring systems, and evaporation studies has revealed the detailed operation of the water cycle and confirmed its crucial role in maintaining atmospheric circulation and suspension. This scientific understanding shows how the water cycle operates as a sophisticated natural system that maintains atmospheric stability while adapting to changing environmental conditions. As you continue to rest peacefully tonight, the water cycle continues its endless circulation around you, lifting moisture into the atmosphere, transporting energy through atmospheric layers, creating circulation patterns that support atmospheric weight, and maintaining the dynamic equilibrium that keeps our sky suspended safely above Earth's surface. The beauty of the water cycle lies in its seamless integration with all other atmospheric processes. It operates simultaneously as a moisture transport system, an energy circulation mechanism, a pressure regulation system, and a circulation driver, demonstrating how natural systems achieve multiple functions through single elegant processes that maintain overall atmospheric stability. Tonight, as water molecules continue their endless atmospheric journey, carrying energy upward through evaporation and releasing it through condensation, creating circulation patterns that support atmospheric suspension while providing the moisture necessary for life on Earth, you can rest securely knowing that this ancient cycle will continue its essential work throughout the night and far into the future, maintaining the atmospheric circulation that keeps our protective sky suspended in its eternal embrace above our living world. As our gentle journey through the science of atmospheric suspension draws toward its peaceful conclusion, we can appreciate the remarkable symphony of forces, processes, and natural systems that work together in perfect harmony to maintain our sky in its suspended state above Earth's surface. This floating equilibrium represents one of nature's most elegant demonstrations of how multiple complex systems can integrate seamlessly to create stability, beauty, and a protective environment that shelters all life on our planet. Picture our atmosphere as it truly exists, not as a simple layer of air resting on Earth's surface, but as a dynamic, living system suspended in perfect balance through the interplay of molecular motion, pressure gradients, thermal circulation, magnetic protection, layered organization, and water cycle dynamics. Each of these systems contributes its essential function to the overall stability that keeps our massive sky floating safely above us, never falling despite its enormous weight, always suspended in its protective embrace around our living world. As you rest comfortably in this moment, you exist within this suspended ocean of air that demonstrates the fundamental principle of balance that governs natural systems. The same way your body maintains balance through the coordination of multiple systems: circulatory, respiratory, nervous, skeletal. Our atmosphere maintains its suspended balance through the coordination of multiple atmospheric systems, each performing specialized functions that support the overall stability of our planetary sky. The molecular dance that creates atmospheric pressure continues around you right now, with trillions of air molecules bouncing against each other and against every surface billions of times per second, creating the constant upward pressure that balances the downward pull of gravity. This molecular activity, powered by thermal energy from the sun and driven by the kinetic motion that characterizes all matter, provides the fundamental foundation for atmospheric suspension by preventing gravitational compression while maintaining the pressure structure that supports atmospheric weight. Consider how perfectly balanced these molecular forces remain. If molecular motion were too energetic, our atmosphere would expand beyond Earth's gravitational control and escape to space. While if molecular motion were insufficient, gravitational compression would collapse our atmosphere into a thin layer against Earth's surface. The actual molecular energy levels maintain exactly the right balance to create stable atmospheric suspension while providing the pressure conditions necessary for life. The gravitational embrace that holds our atmosphere close to Earth demonstrates how apparent opposites can work together to create beneficial stability. Gravity's downward pull provides the organizing force that prevents atmospheric escape while creating the pressure gradients that drive circulation, while molecular motion's outward pressure provides the resistance that prevents atmospheric collapse while maintaining the suspended structure that keeps our sky aloft. Picture this gravitational balance as a gentle embrace that holds without crushing, contains without constraining, organizes without rigidity. The gravitational field that surrounds Earth creates the perfect balance of attraction and freedom that allows our atmosphere to remain securely suspended while maintaining the dynamic circulation necessary for atmospheric health and stability. The thermal circulation that drives atmospheric movement represents perhaps the most beautiful aspect of atmospheric balance, with solar energy creating temperature differences that generate circulation patterns spanning from small convective cells rising from sun-warmed surfaces to global circulation systems that distribute energy and atmospheric mass around the entire planet. This thermal engine operates with perfect efficiency, converting solar energy into atmospheric motion while maintaining the circulation patterns that support atmospheric suspension. The layered structure of our atmosphere demonstrates how natural systems achieve both stability and functionality through organized complexity. Each atmospheric layer, troposphere, stratosphere, mesosphere, thermosphere, contributes specialized functions to overall atmospheric stability while depending on other layers for support and circulation connectivity. This layered organization provides both structural strength and operational flexibility, maintaining atmospheric suspension while allowing adaptive responses to changing conditions. Imagine these atmospheric layers as floors in an invisible building where each level supports those above while being supported by those below, with elevators of thermal circulation connecting all levels and allowing movement of atmospheric mass and energy throughout the vertical structure. This architectural organization maintains structural integrity while providing the circulation pathways necessary for atmospheric health. The magnetic shield that protects our atmosphere from solar wind erosion operates continuously and invisibly, deflecting charged particles that could otherwise gradually strip away atmospheric mass over geological time. This magnetic protection ensures that the atmospheric mass essential for maintaining suspension remains safely within Earth's gravitational influence, providing long-term stability that allows other atmospheric processes to operate without concern for atmospheric loss. The water cycle that moves moisture and energy through our atmosphere adds biological connectivity to atmospheric circulation while demonstrating how life on Earth participates in maintaining atmospheric stability. The endless circulation of water vapor through evaporation, atmospheric transport, condensation, and precipitation creates energy transport and circulation patterns that support atmospheric suspension while providing the moisture necessary for terrestrial life. Picture the water cycle as the circulatory system of our atmospheric body, carrying energy and materials where needed while maintaining the circulation that keeps our atmospheric organism healthy and stable. This biological metaphor reflects the living nature of our atmospheric system, which responds and adapts to changing conditions while maintaining the essential functions that support atmospheric suspension. The integration of all these atmospheric systems creates emergent properties that exceed the sum of individual system capabilities. Molecular motion alone could not maintain atmospheric suspension without thermal energy to drive it. Thermal circulation could not operate without pressure gradients to organize it. Pressure gradients could not exist without molecular motion to create them. And the entire system requires magnetic protection and water cycle energy transport to maintain long-term stability. This system's integration demonstrates one of the most important principles of atmospheric suspension. Stability emerges from the interaction of multiple systems rather than from the dominance of any single system. No individual atmospheric process could maintain suspension independently, but the coordination of multiple processes creates robust stability that can adapt to changing conditions while maintaining essential atmospheric functions. Consider how this atmospheric balance has persisted for billions of years despite countless environmental changes, planetary impacts, volcanic eruptions, ice ages, and other disturbances. The balance that maintains atmospheric suspension operates through dynamic stability rather than rigid resistance, allowing adaptive responses to environmental changes while maintaining the fundamental atmospheric structure that supports life. The research conducted by atmospheric scientists using satellites, weather balloons, computer modeling, and ground-based measurements has revealed the sophisticated beauty of atmospheric balance while confirming the remarkable stability and efficiency of natural atmospheric systems. This scientific understanding helps us appreciate both the complexity and the elegance of the atmospheric processes that maintain suspension while showing how human activities interact with natural atmospheric systems. As you breathe slowly and naturally in this peaceful moment, you're participating directly in the atmospheric balance that maintains suspension. Each breath removes oxygen from atmospheric circulation while adding carbon dioxide and water vapor, creating tiny contributions to atmospheric composition and circulation that become part of the global atmospheric system. Your breathing connects you intimately to the atmospheric processes that keep our sky suspended safely above us. The atmospheric balance that maintains suspension also creates the stable environment necessary for the development and continuation of life on Earth. The same processes that keep our sky from falling also maintain atmospheric pressure suitable for respiration, atmospheric composition suitable for biological processes, atmospheric circulation that distributes heat and moisture, and atmospheric protection from harmful radiation and space particles. This connection between atmospheric suspension and biological support demonstrates how natural systems often achieve multiple beneficial functions through single elegant processes. The atmospheric balance that prevents our sky from falling simultaneously creates the environmental conditions that allow life to flourish, showing how natural efficiency integrates multiple requirements into unified solutions. The beauty of atmospheric balance lies in its effortless operation. You never have to think about maintaining atmospheric suspension, never need to monitor atmospheric processes, never require conscious effort to keep our sky aloft. The natural systems that maintain atmospheric balance operate automatically and continuously, providing reliable atmospheric stability while you focus on living your life within the protected environment they create. This automatic operation reflects the fundamental wisdom embedded in natural systems, which achieve complex functions through processes that operate according to universal physical laws rather than requiring conscious control or external management. The atmospheric balance that maintains suspension demonstrates how natural systems can be simultaneously complex and simple, sophisticated and effortless. As night settles more deeply around you and sleep begins to approach, you can rest in the profound security provided by atmospheric balance. The same forces and processes that have maintained atmospheric suspension for billions of years will continue their essential work throughout the night, ensuring that you wake tomorrow beneath the same protective sky that has sheltered life on Earth since the beginning. The atmospheric systems that maintain suspension operate on timescales that dwarf human experience. Molecular motion that occurs billions of times per second, circulation patterns that develop over days and weeks, seasonal cycles that span months, climate patterns that persist for years, and atmospheric evolution that continues over geological eras. This multi-scale temporal operation ensures atmospheric stability across all time periods relevant to human life and beyond. Tonight, as you prepare to surrender to sleep, you can appreciate the magnificent suspended ocean of air that surrounds and protects you. 5.5 quadrillion tons of atmosphere float above you in perfect balance, held aloft not by any solid support, but by the elegant integration of natural forces that demonstrate the fundamental harmony underlying all natural systems. The atmospheric suspension that keeps our sky from falling represents perhaps the most beautiful example of natural balance on our planet. Complex enough to fascinate scientists, stable enough to support life for billions of years, elegant enough to inspire wonder, and reliable enough to provide the security that allows peaceful sleep beneath our floating sky. Rest peacefully tonight, knowing that atmospheric balance will maintain its ancient vigil, keeping our protective sky suspended safely above you while you sleep, ensuring that you wake refreshed beneath the same floating ocean of air that has cradled humanity throughout history and will continue to shelter life on Earth far into the future. As consciousness gently fades and sleep approaches, let the knowledge of atmospheric suspension provide comfort and security. Our sky will never fall because it floats in perfect balance, suspended not by magic, but by the elegant science of natural harmony that demonstrates the fundamental beauty underlying our living world. Sweet dreams beneath our floating sky. Underscore Thank you for joining me on this peaceful journey through the science of atmospheric suspension. If this gentle exploration of why our sky never falls has helped ease you toward restful sleep, I hope you'll consider subscribing to The Drowsy Professor for more soothing science that transforms complex natural phenomena into bedtime stories that inform while they comfort. Hit that subscribe button and ring the notification bell to discover more fascinating science designed specifically for peaceful nights. From the mysteries of deep ocean currents to the hidden mechanics of planetary motion, each episode crafted to satisfy your curiosity while guiding you gently toward restorative sleep. Share this video with anyone who might enjoy learning fascinating science while drifting off to dreamland. And let me know in the comments what scientific mysteries you'd like to explore in future episodes. Until next time, sleep well beneath our beautifully suspended sky. And remember, science is most wonderful when it helps us rest peacefully in the knowledge that our natural world operates with elegant perfection all around us. Good night, and thank you for choosing The Drowsy Professor for your journey into the soothing science of sleep.